Hello, everyone. Welcome to the mini lecture on theoretical mechanics. In the last lesson, we have learned the theorem of composition of velocities of point together. Do you remember? When we stand on a rotating plane and observe a moving object, its velocity is the vector sum of relative velocity and transport velocity. So, what about acceleration? Is it right to just add it up? Today, we are going to challenge a very fascinating and even mysterious point of knowledge in theoretical mechanics, Coriolis acceleration. You may have heard that the rivers in the northern hemisphere always wash harder on the right bank, or white typhoons always spiral, and the hidden force behind these natural phenomena is the thing we are going to discuss today. First of all, let's review the old and learn the new. Before studying the complex composite motion, we review the basic fixed axis rotation of rigid bodies. Please look at the formula on the screen. When a rigid body rotates about a fixed axis, the velocity of any point m in the rigid body can be expressed by vector product, that is, cross product. We take any point O on the axis as the origin, and the position vector of point m is vector r. Its velocity vector v equals the angular velocity vector omega cross the position vector vector r. This formula tells us in a concise way that the magnitude of the velocity is proportional to the distance, and the direction is perpendicular to the plane formed by vector omega and vector r. Next, look at the acceleration. Acceleration is the time derivative of velocity. According to the rule of multiplication of derivatives, we derive the vector omega times vector r and get two terms. The first term is the angular acceleration vector epsilon cross the vector r, which corresponds to the tangential acceleration. The second term is the angular velocity vector omega cross the velocity vector v. Please observe the vector relationship in the figure. Vector omega times vector v. This term actually points to the center of rotation, which is the normal acceleration we've learned before. This review is critical, as it lays the groundwork for our subsequent derivation of the Coriolis acceleration. Namely, a new term arises in the acceleration from the coupling between rotation and velocity. Now we formally introduce the theorem of composition of accelerations when the transport motion is rotation. When the moving frame rotates relative to the fixed frame, the absolute acceleration of the point is no longer just a simple superposition of the transport acceleration and the relative acceleration. After rigorous mathematical proof, an additional term appears in the general form of the theorem of composition of accelerations. The Coriolis acceleration, which we denote by AC. What is Coriolis acceleration? Its vector expression is shown above. The vector omega e here is the transport angular velocity of the kinetic system, where vector vr denotes the relative velocity of the moving point with respect to the moving frame. Note that this acceleration is due to the intercoupling of the rotation of the transport motion with the relative motion of the moving point. Regarding the magnitude of Coriolis acceleration, we should keep this formula in mind. AC equals 2 times the transport angular velocity multiplied by the relative velocity and multiplied by the sine value of the angle theta between them. As for direction, we still use the right-hand rule. Turn the four fingers of the right hand from the direction of transport angular velocity to the direction of relative velocity at an angle less than 180 degrees. The direction of the thumb is the direction of Coriolis acceleration. There is a special case to be noted. If the transport motion is translation, then the transport angular velocity is equal to 0, and the Coriolis acceleration disappears at this time. It explains why in the previous chapter of translation, we didn't mention it. In practical engineering problems, we often need to judge whether the Coriolis acceleration is equal to 0. According to the formula, there are three main cases where the Coriolis acceleration is equal to 0. 1. The transport motion is translation. For example, the moving reference frame is fixed on a train traveling in a straight line. 2. The relative velocity is 0. Now, the moving point is instantaneously stationary relative to the moving frame. 3. The transport angular velocity is parallel to the relative velocity. Look at this spherical model on the screen. Suppose that the Earth rotates around the z-axis of its rotation axis. If we observe an object moving along the meridian to the north or south pole, at that instant, its movement direction is exactly parallel to the Earth's rotation axis, at which point the Coriolis acceleration is equal to 0. But at other latitudes, as long as your direction of motion is not parallel to the axis, the Coriolis force will push you to one side. In the northern hemisphere, this force deflects objects to the right. In the southern hemisphere, it is to the left. This is the reason why cyclones in northern hemisphere always turn counterclockwise. Theory must be combined with practice. Let's look at a classic engineering case. The quick return mechanism of the planer. As shown, the crank OA rotates at a uniform angular velocity omega about the fixed axis O. The slider A is connected to the end of the crank by a hinge, and at the same time the slider A slides on the rocker O1B. This structure can convert circular motion into oscillation. The topic gives the crank length OA equals R. The center distance between the two axes O01 equals L. What we need to ask is, what is the angular acceleration alpha 1 of the rocker O1B when the crank is in the horizontal position? This is a typical problem involving rotational transport motion, and Coriolis acceleration must not be ignored here. The first step in solving the acceleration problem is always velocity analysis. 1. Select the moving point, moving frame, and fixed frame. We choose the slider A as the moving point. The moving frame O1x prime, y prime is fixed to the rocker O1B, while the fixed frame is fixed to the base. 2. Decompose the velocity vector. Absolute velocity. The slider rotates with the crank about point O. Its direction is perpendicular to OA, and its magnitude is equal to omega multiplied by R. Transport velocity. It is the rotation velocity of the point on the rocker that coincides with point A, and the direction is perpendicular to O1A. Relative velocity. The sliding velocity of the slider along the rocker O1B, with the direction along the axis O1B. According to the theorem of composition of velocities, by geometric projection, we can find the relative velocity and the transport angular velocity at this instant. These data will serve as the basis for the next step in calculating the acceleration. Now move to the core link. Acceleration analysis. According to the theorem of composition of accelerations, the absolute acceleration equals the vector sum of the transport acceleration, the relative acceleration, and the Coriolis acceleration. 1. Absolute acceleration. Because the crank rotates at a constant speed, there is only normal acceleration, pointing to point O, and the magnitude is omega squared r. 2. Transport acceleration. Because the rocker is rotating, the transport acceleration is divided into tangential component and normal component, wherein the normal component is calculated from the obtained omega 1. The tangential component contains the angular acceleration alpha 1 we want. 3. Relative acceleration. The acceleration of the slider sliding along the rocker, directed along the rocker with unknown magnitude. 4. Coriolis acceleration. This is the key part. AC equals 2 omega 1 VR. How to judge its direction? Turn VR 90 degrees in the direction in which the rocker rotates, i.e., the direction of omega 1, and the result is the direction of vector AC. With a vector analysis graph, the last step is to establish a coordinate system for projection. We project the equation of composition of accelerations into the x-axis perpendicular to the rocker. The cleverness of this approach lies in that the unknown relative acceleration AR can be cancelled out directly. Substitute all previously analyzed values into the projection equations to solve for the tangential acceleration of the rocker, and further calculate its angular acceleration. The calculated result shows that alpha 1 is positive value, indicating that its direction is consistent with what we assumed, that is, turning counterclockwise. Through this example, you can see that if we don't consider Coriolis acceleration, it will lead to substantial errors in our results. In precision mechanical design, such deviations can be fatal. Next, we look at a more challenging example. Valve cam mechanism. The cam rotates at a constant angular velocity omega 0 about the fixed axis O, pushing the tappet upward. The topic gives the geometric parameters at this time. OA equals r, the radius of curvature of contact point A is ρ, and the angle between the normal and OA is theta. Our objective is to find the absolute acceleration of the tappet at this instant. First, we should identify three types of motions. Moving point. Select the endpoint A of the tappet. Moving frame. Fixed to the cam. Absolute motion. The tappet is constrained by the guide rail and can only do linear motion along the vertical axis. Relative motion. If you sit on the cam unobserved, you will notice point A is sliding along the profile curve of the cam. Transport motion. The moving frame rotates on a fixed axis with the cam. In the velocity vector figure, the absolute velocity is vertically upward. The transport velocity is pointed to the right perpendicular to the OA. The relative velocity is in the tangent direction of the cam profile. Using the theorem of composition of velocities, we can find the relative velocity according to the geometric relationship. This VR will directly affect the magnitude of the subsequent Coriolis acceleration. Acceleration analysis is the most critical part. Note that the relative trajectory of motion here is a curve, so the relative acceleration will have a normal component. Absolute acceleration. The acceleration of the tappet we want to calculate. The direction is vertical. Transport acceleration. The cam rotates at a constant angular velocity, so it only has centripetal acceleration directed toward point O. The relative acceleration is divided into tangential and normal directions. Its normal component points toward the center of curvature of the profile. Coriolis acceleration AC equals 2 omega 0 VR. We project these vectors onto the normal n of the contact point. After a series of algebraic operations, we get the expression for the absolute acceleration. Look at this result formula, which includes the radius of curvature, rotational speed, and geometric angle. It tells us that the acceleration of the tappet depends not only on how fast the cam turns, but also on what the cam looks like, curvature, and where it is currently in contact. Alright, this lesson is closing to the end. The acceleration analysis for solving problems of composite motion of a point follows definite rules. I summarized the 5-step approach. 1. Select the objects. Select the moving point and the moving frame. It is the key to success. 2. Analysis of movement. Distinguish the three kinds of movement properties: absolute, relative, and transport. 3. Solve the velocity. First, make the velocity diagram and find the BR and omega E, because they are the raw materials for Coriolis acceleration. 4. Cloth vector. Draw all acceleration vectors according to the formula vector AA equals vector AE, plus vector AR, plus vector AC. Don't forget Coriolis acceleration. 5. List the projection. Select the appropriate axis, usually the axis perpendicular to the unknown quantity, to solve the projection. Coriolis acceleration is not just a mathematical term, it is a balancing force in nature. From huge ocean current cyclones, to sophisticated aerospace gyroscopes, to even sliders on planers, it's everywhere. Seek moving quantities within moving frames. Combine vectors yet remain distinct. Mastering the essence of composite motion gives you the ability to see and quantify the world from different perspectives. I hope you can practice more after class and really master the Coriolis acceleration. Today's lesson ends here. Thank you. See you next time.